Today, we're going to delve into a subject that is far too often overlooked but critically important to our success as growers. That subject is how to match fertilizers to the chemistry of the water source available to us. Generally, we will have one of two types of water available to us. The first being what we'll call ground-based water. That's water from a municipal well or reservoir, or water from our own dug or drilled well. The second type of water is what we'll call pure water. That's water from an RO or reverse osmosis process, distilled water, rainwater, and some very pure water from certain wells and springs. You might ask, what difference does it make where my water comes from? The answer is simple, that different waters have dramatically different chemistries. And a nutrient or fertilizer that we choose to use with one type of water that may work very well with another type of water with a different chemistry may actually work to the detriment of the plant. A nutrient or fertilizer that works well with one water can actually cause deficiencies, toxicities, or nutrient lockout with another type of water. So let's take a look at what this might mean for us as growers. First, let's take a look at these ground-based water sources. These can either be from municipal supplies like a reservoir or a municipal well, or from our own dug or drilled wells. This type of water has been in contact with the ground, traveling through the ground matrix, and as that water travels through the ground matrix, it actually will dissolve and pick up some of the minerals in the rock that it is traveling through. And these minerals now end up in suspension, in solution in the water. And some of these minerals we're very familiar with: nitrogen, phosphorus, potassium, magnesium, sulfur, iron, calcium, sodium, and a whole bunch of others. And these can be visible to you when you see those rings and deposits in your sink and your bathtub and your toilet. This water now can contain either high concentration of these soluble minerals, low concentrations, or anything in between. And we can measure that concentration with a meter called an EC meter. Some of you may have watched some of my other videos on EC meters, how they work and how they actually measure these mineral ion concentrations in our water. And some of these dissolved minerals are also able to be taken up by your plants as nutrients. In addition to the minerals that are dissolved in the water, we have to look at a couple other critical factors when we start looking at the interaction between your water and the fertilizer that you choose. The first of these factors is the factor known as alkalinity. So what is alkalinity? Alkalinity is the buffering capacity of that water. It's a measure of the ability of the water to neutralize acids and bases. And here's the important part of the definition: and thus maintain a fairly stable pH level. You are all familiar with the importance of measuring your pH and trying to keep it within a certain range for the health of your plant, because an improper pH range can cause uptake and lockout problems. So we know that pH is critical in our grow program, and now we know that alkalinity is a key factor in being able to control that pH. So alkalinity, the capacity of the water to neutralize both acids and bases and keep them in a stable range. So what does alkalinity measure? When we have a lab test done, what they're measuring is the carbon dioxide, bicarbonate, carbonate, and hydroxide levels within that water. The second key part that we need to consider, in addition to the individual mineral salts, is pH. And we're all familiar with measuring pH of our nutrient solutions, using pH tapes, using EC and pH meters. So we all know how important pH is. But what is pH? pH stands for potential hydrogen. And in a nutshell, it is a measure of the hydrogen ions, those H positive ions, in that solution. It's measured on a scale that goes from 0 to 14, and a pH of 7 is what we call neutral. Now, as the pH number drops, say from 7 to 6, 6 to 5, 5 to 4, that means that the number of free hydrogen ions present in that solution is increasing. You would think that as the pH drops, the number of ions would drop, but the way that we calculate the pH is actually in an inverse formula, which just means that the end product ends up that as the pH drops, it means that the hydrogen ions are increasing. So as the hydrogen ions increase, the pH drops and the solution is more acidic. So conversely, as the pH rises, the number of hydrogen ions in that solution is decreasing, and the solution becomes what we call more basic or alkaline. And remember that maintaining a proper balance between this acid and base is what allows us to maintain a proper pH range for both the nutrient solution and the grow medium that we're growing our plants in. And now we're going to look at how choosing the right fertilizer formulation can actually dramatically impact this balance between acids and bases and our ability to reach and maintain that pH that we want to have for our plants. First, let's look at these two different water samples. The water sample on the left is rainwater. The water sample on the right is a well water. Let's look at the two issues that we were just talking about, pH and alkalinity. We can see that they differ dramatically. On the left, the rainwater sample, we have a pH of 5.31. We know that this is quite acidic. On the right, from the well water, we have a pH level of 7.14, which is actually quite alkaline, and we would like something in between. And correspondingly, if we look at the rainwater with a low pH, we can see that the alkalinity, or the ability of that water to neutralize acids, is very low. On the right, the alkalinity is very high, which would automatically indicate to us that the pH is probably going to be high because we have a high abundance of ions that are going to neutralize the acids and correspondingly make our pH go up. So to help us prevent potential problems during our grow operation through the season, this indicates to us that we may want to make slightly different fertilizer choices dependent upon the lab results that we've just gotten for these two different water samples. So let's take a quick look at this, at what this might translate to for us. When we fertilize a plant, we know that one of the major nutrients that we want to supply, one of those macronutrients, is nitrogen. When we look at a bottle or a bag of fertilizer and we see those three numbers on the front, those three numbers represent nitrogen, phosphorus, and potassium, the amount within that fertilizer. And the first one is nitrogen, and it's the most widely used nutrient that we provide to our plants. But nitrogen is found in three primary different forms in fertilizers, and the form that that nitrogen is in can actually affect our ability to control our pH in both our nutrient tanks and in the grow medium. So let's look at those three different types of nutrient. First, we have ammonium, the ammonium form of nitrogen. And you can see that it's nitrogen bound with 4 hydrogen ions. Then we have nitrate, and you can see here the chemical configuration is very different. We now don't have the hydrogen, we have the O3 component, the hydroxide component. Then we have urea nitrogen. So what happens when we use these different forms of nitrogen? In very simplistic forms, we're not going to submit these for evaluation by an organic chemist, but this is in a nutshell what you can think of when we give these three different forms. If we first look at ammonium, ammonium can be taken up by the root in solution, but because of a lot of different organic chemistry and chemistry principles within the plant doesn't want to retain all this extra hydrogen, so it spits it out. Not a really good solid science term, but we'll think about it as the root spitting out the extra hydrogen ions here. If we remember from the last slide, as the hydrogen ions increase in solution, and that solution being outside of the plant roots and in the grow medium, those excess hydrogen ions will cause the pH outside of the roots to drop. The environment outside of the root now in the grow medium and the water in that grow medium, that pH will drop. It's becoming more acidic. If we look at the nitrate nitrogen, the plant can take up the nitrate. It's basically looking for the nitrogen. So again, to maintain an internal chemical balance, it will spit out the OH ions. Those OH, we remember, as those ions increase, the pH will increase. This is neutralizing the acids outside. So as the OH increases, it means a subsequent decrease in the hydrogen ions outside. So the pH is going to increase in the solution and the grow medium. If we look at the urea, urea can either enter the roots in its original chemical configuration, or in the soil or the grow medium, it can easily convert to ammonium. The root can take that out, but once again, it will spit out the excess hydrogen ions. The excess hydrogen ions increase in concentration, which drives the pH again down. It becomes more acidic. So we can see what's going to happen if we use an ammonium-based fertilizer. That will increase the number of hydrogen ions, which will decrease the pH. If we use the nitrate form, it will increase the OH ions, which will cause an increase in pH. And again, the urea will cause a decrease in the solution and the grow medium outside. So our choice of fertilizers and the choice of what type of nitrate or ammonium or urea we deliver to that plant can dramatically affect the pH in the solution, the water outside the roots, and that pH of our grow medium. And our target as growers is having a pH in the range of 5.8 to 6.5. In the previous slide, we were looking at a lab result for a fairly common well water, and we saw that the pH was quite high, over 7, and the alkalinity was quite high. In this sample, we're looking at rainwater, and now we're seeing a very different situation. Here, we're looking at a pH at 5.31, which is, again, quite low. The water is acidic, and we're looking at correspondingly a low alkalinity. And as we saw on the previous slide, our choice of fertilizer and the form of the nitrogen within that fertilizer can quite dramatically affect our ability to control the pH in both the solution and the grow medium. In the past, or the previous slide, a use of an ammonium nitrogen, which would then release or spit out the hydrogen ions, which would cause a drop in the pH, is something that we would look as beneficial to bring that pH from 7 maybe down to that 6 range. If we used that same ammonium nitrate in this rainwater and had the corresponding spitting out of the hydrogen ions, which would increase the hydrogen ion concentration in the solution around the roots and the grow medium, we would exacerbate the low pH and actually cause that pH to drop even further. So instead of using an ammonium nitrogen form, what we would want to do is use a nitrate form, which is the NO3 form, so that when the roots took up that nitrate and then spit out the OH, the hydroxide, that spitting out of the OH would neutralize hydrogen ions on the outside and thus raise the pH, which is what we were looking for. And that would help us stabilize this low pH and allow us to better control it and keep a better environment in our grow medium. So a thing to keep in mind when you go to the store and buy a pH up product, you can understand now what that product is. You're delivering a product that is going to increase the OH ions in solution. That's why you can use something as simple as a baking soda that will increase the OH ions to give you a very simple way of raising the pH. When we buy a pH down product, you're adding a product that will add hydrogen ions, generally an acid. A common acid used in commercial operations is just straight up battery acid, sulfuric acid. So that's all that pH up and pH down products are doing. And you can see where our choice of the nitrogen form, we're doing the same thing. So we do have the ability to control pH to a certain degree by our choice of fertilizer. So how do nutrients fit into all of this that we've been talking about? So first, let's look at a couple of simple basic concepts around optimal nutrient delivery to our plants. The first is we want to choose a fertilizer that is complete. And by complete, we mean containing all the macro, secondary, and micronutrients needed by the plants we are growing. We may be able to find a single product that is complete, but that's generally not the rule in a commercial operation because of the special needs of most of the plants that we're growing. In such a situation, we may be using what we call a fertilizer program that will be one or two particular products in the vegetative phase, and then as we switch to fruiting, whether it's tomatoes, peppers, high value crops, we change to another combination of products that will deliver the exact precision level of nutrients that we know that those plants need. Another critically important concept in fertilizers is a fertilizer has to be balanced. And by balanced, we mean that all of the nutrient salts in that fertilizer are in the proper ratio to each other. We can't just take a handful of nitrogen and a handful of potassium and a handful of magnesium and throw them all into a bag and let the plant take what it needs and not use the excess. Too much of one nutrient, and this is critically important, too much of one nutrient can act as an antagonist to a singular or multiple nutrients within that nutrient solution. For example, if we have a nutrient solution that has too much potassium in it, that excess of potassium can actually result in symptoms of calcium and or magnesium and or nitrogen deficiency in our plants, even if the calcium, magnesium, and nitrogen are present in sufficient amounts. It's the excess of the potassium that actually acts as an antagonist. We can see this happen very commonly when growers decide to just crank up their levels of phosphorus or potassium at a particular point in their grows, no matter what their crop is, thinking that it's a good thing, but it may actually end up being quite problematic. We know that a change in water and grow medium pH can cause deficiency and toxicity or lockout problems, and we just saw that our choice of fertilizer can greatly affect the pH in our grow medium. Different plant species and varieties have different nutritional requirements. One fertilizer that may be perfect for certain varieties and species of plants may be detrimental to another type of plant. And we know from decades of scientific research and data that the delivery systems and the requirements of different plants are well recorded, and that we can see those in the feed schedules from different manufacturers. If we're growing tomatoes, we can get the feed schedules that will tell us precisely how much of each individual nutrient that plant needs at its particular life stage. So feed schedules are something that are critically important to us if we're going to grow optimally. So let's take this a step further. And we've already looked at pH and alkalinity and how they can affect what goes on in our soils and grow mediums and the effect that they have on our plants, either in a positive or detrimental way. So let's look at nutrients, and let's pick a singular nutrient as an example and see how water chemistry can positively or negatively impact our plant's ability to uptake and use different nutrients. Let's take, for example, calcium, and calcium is critically important for most plants, everything from lettuce, tomatoes, peppers, to high-value medicinals. We know from years of research the levels of calcium that most crops need, be they flower, food, or high-value crops. And as an example, we can look at a tomato plant. And in general, depending on the life stage of the tomato, we would want to deliver somewhere between, say, 125 to 200 parts per million of calcium at the different life stages. So how do we do this? First, as we said in the previous slide, we want to find a complete and balanced fertilizer or a fertilizer program that's appropriate for the production of tomatoes. Second, and this is something to really understand, that if we're trying to deliver 125 parts per million of calcium, just as an example, that tomato plant needs, that 125 parts per million of calcium is the sum of the calcium both in the fertilizer and the calcium that's what we call on board or already dissolved and available in your water source. And we as growers then need to know both these numbers. If we don't understand that if our fertilizer is going to deliver 100, 150 parts per million of calcium, and there's already 100 parts per million in the calcium, we have to understand that this added level of calcium might be too much for our particular plants. So we have to understand that the calcium that we know from scientific data or any other nutrient that is needed by the plant at that life stage is an addition of what's present in the water that we're going to be using and that's going to be added by the fertilizer that we choose. So let's take a look at a couple of examples of this. First, I'll ask you to just remember that we could either be using groundwater with some or plenty free nutrients on board, or pure water with little or no free nutrients on board. Our goal is to make sure we deliver the right level of each nutrient, and to remember that we may use something like a rainwater or a RO water, which might have, in this case, 0 parts per million calcium on board, or we may be using a ground-based water source with 60, 70, 80 parts per million calcium or more. So let's take a look at what might happen as we choose different types of fertilizers. First, I'm picking the example of using a water that many of us will be using, a well water or municipal water that might contain somewhere in that 50, 60 parts per million calcium already on board. And I'm going to use as an example a few different varieties of Jack's fertilizers. I personally use Jack's in my commercial operations for Just one or two simple reasons. They're rooted in science, and I can't find a better product for the money that you pay to buy a nutrient program. So let's look at one or two examples. First, let's look at a very popular Jack's fertilizer, the Jack's 10-30-20. Again, widely used, wonderful fertilizer. If we mix it at the level of, say, a teaspoon and a half per gallon, which will give us about 225 parts per million of nitrogen, which is the range of nitrogen we'll use on average for most of the plants we'll grow in our gardens or in greenhouses in their mature, active growing stage. But Jack's 10-30-20 contains no onboard calcium. So when we look at this mixture that we're going to feed our tomato with, and remember our goal for our tomato is to be somewhere in that 125 parts per million calcium for that plant. If we take this Jack's with 0 and we add that to the 60 parts per million on board in the water, we get 0 plus 60. We end up with 60 parts per million calcium delivered to that tomato plant. Not real good in terms of making that tomato plant really happy. Let's look at a second example. Say of using the Jack's 15-5-20, another example of a widely used fertilizer. If we mix it at the level of, say, a teaspoon per gallon, giving us a 200 parts per million nitrogen range, the fertilizer alone will deliver around 45 parts per million calcium. The water will deliver 60 parts per million. That's the onboard calcium in our municipal or well water. So we get 60 plus 45. So we'll be delivering somewhere in that 105 parts per million calcium to our tomato plant. Not quite where we'd like to be, but it's not bad. It's one that you could probably get away with. Let's look at a third example. This would be Jack's 12-4-16. If we mix it at a rate of, say, a teaspoon and a quarter per gallon, that'll give us around 200 parts per million nitrogen. And this product, just through the fertilizer, will deliver around 130 parts per million calcium. If we add that 130 to the 60 in the water, we're going to be at around 190 parts per million calcium, and your tomato is basically going to give you a big thumbs up. And one of the reasons we're looking at calcium in relation to tomato plants is that a deficiency in calcium can cause that dreaded blossom end rot on calcium. So delivering a sufficient level of calcium to tomato plants is crucial for our ability to bring in a successful crop. So example 1, using a well water or municipal water with 60 parts of calcium. If we look at a second example of using rainwater, I use rainwater in my operation. A lot of you use rainwater out there. We've seen from the lab tests that rainwater contains virtually no calcium, so we'll consider it as 0 parts per million calcium, and this would be the same for RO water. If we look at the first example again with a Jack's 10-30-20, we have 0 through the Jack's, 0 through the fertilizer. We're going to be at 0 delivery of calcium to that tomato. We look at the second choice again, the 15-5-20. We mix it at the same concentration. We're going to have about 45 parts per million calcium through the fertilizer, 0 through the water. Not going to be good. We're going to end up with a level of about 45 parts per million calcium. We look at the Jack's 12-4-16. Again, mixing it at that teaspoon to teaspoon and a quarter per gallon. We get 130 from the 12-4-16, 0 from the water. We're at 130 being delivered to the tomato. Again, that tomato's probably going to be quite happy. We can look at the last example here being a well water that is quite common, a well or municipal water, which might be in a low calcium concentration rating of maybe 40 parts per million or a little lower than that. We'll use the same three examples again. 0 from the 10, 30, 20, 40 from the water, giving us a total of 40 for the tomato. Again, not our best choice. The 15, 5, 20, we're going to get 45 from the fertilizer, 40 from the water, giving us 95 total. Not bad. We could probably get away with that. The 12, 4, 16 again, 130 plus 40 from the water, 170. Again, a thumbs up from your tomato plants. So how do we put all of this together? First, we'll look at something like a Jack's nutrient line. Some people would look at Jack's and say, they just have too many different formulations. It gets me confused. I want to use one of the generic 1 teaspoon of this and just water anything. From a standpoint of a serious grower or a science-based grower or somebody who's just looking for maximal productivity, maximum quality from whatever it is that you're growing, the fact that a company like Jack's has a multitude of choices should be reassuring to you from the standpoint that there are so many choices because water chemistry changes, the plants that we're growing and their needs change, and we have a far greater ability to pick a precision combination that will put us exactly where we want to be for the plants that we're growing. So this multitude of choices is a very positive thing because it allows us to hone into a very precise combination of the fertilizer that we choose matched with the water chemistry that we're going to be using. And that is going to give us maximal results. You might ask, why was there no calcium in the 10, 30, 20? The answer relates to what we were just talking about, that the 10, 30, 20, which is a highly respected fertilizer, is not meant to be a one and done product. It's part of a fertilizer system for plants in their different phases, and the 10, 30, 20 is focused at that transition from a vegetative to bloom to fruit production. And so its formulation is scientifically based on what it's meant to do at that time. So when we look at all of these choices, all of these combinations of water chemistry, what it really boils down to, if you're a serious grower and you're looking for maximal results, it's upon us to understand this basic and not really complex science that we've been talking about to help us maximize our results, whether it's in our tomato garden or growing our peppers or our flowers on our deck or our high value commercial operations. This is what's going to allow us to be at that optimal production level. And calcium's not the only nutrient we need to keep in mind when we talk about all of these decisions. Every nutrient that we see on the water tests, we could talk about in the same way. As a last example or two, let's just revisit a couple of the water samples that we looked at before. This sample is rainwater. And I bring this up because rainwater, in addition to many of the well and municipal samples that we see, will show very low levels of a number of nutrients, one of those being sulfur, as you can see over here on the left. Sulfur isn't used heavily by plants, but it's critical in a lot of different chemical reactions that happen. If we look at tomatoes, for example, which we've been talking about, a tomato that's grown in a sulfur deficient or a sulfur free environment will basically lack flavor because the sulfur is very critical in those chemical compounds which we perceive as odor and flavor. As a result of that, a company such as Jack's that's rooted in science, when they're making recommendations after looking at different water samples, they will very often recommend the periodic addition of small amounts of Epsom salts. You'll see this quite commonly, which is magnesium sulfate, and that's where the sulfur is coming from, to make up for the deficiency in most waters. So again, we get back to this looking at the lab results, seeing where we are, and then fine-tuning our choice of nutrient inputs with our water chemistry to make sure that we're delivering that optimal level of nutrition to our plants. A very last example, and this is one critical to the commercial operations that grow high value crops. This summer I was called to a grow operation to look at some issues they were having. When we looked at the paperwork, the nutrient feed schedule they were following, the environmental conditions, there was nothing that really stood out as blatant to cause the problems that I was seeing. Then I asked to see their lab results from the water tests, and they said they hadn't had one done. So we immediately submitted one, and this is what we got back from the lab. And you can see here that the problem became very clear. Chloride is another one of those minerals that is not used heavily by a plant, but necessary. But plants are also very sensitive to it being present in excessive levels. One of the problems with chloride is that it can really interrupt and disrupt a lot of the biological functions that that plant is undergoing. And a couple of the key reactions that it will displace are the uptake of nitrate and phosphate, two critically important processes during the growth of our plants. The more we looked at where the problem might be arising from, they were drawing from a shallow dug well that was fairly close to a busy road that was heavily treated with salt in the winter, and we were seeing the probable incursion of the road salt into their groundwater base, and they were drawing that and using it in their grow operation. And you can see the levels being far higher than were healthy for that plant. As soon as we switched them to a water source from a deeper well that showed a chloride level within acceptable boundaries, the problems disappeared. A thing to keep in mind for any of you indoor growers is to make sure that the water that you're using to water and feed your plants, make sure that that water is not going through a water softening unit. Water softening units are what we call ion exchange units, that within the softening unit, the process is to draw out minerals such as magnesium and replace it with something in this ion exchange. And the thing that it is replaced with is sodium and the chloride. So the salt level, the chloride level that comes out of a water softening unit is way higher than you want to be using on your plant growing operation. So let's have some final thoughts. First, and you can tell this one was coming, have your water tested. It's the only way we know how to put you in that optimal range in your plant growing endeavors. Go over those lab results with either the lab or a knowledgeable science-based resource, and let me repeat that, a knowledgeable science-based resource at your garden center or grow store. Choose the correct fertilizer program based on the lab results and the particular plants you are growing. Follow the feed schedule. Don't modify it because your buddy told you to modify it. Get and use an EC meter. Reach out to the lab or the science resource when or if you have any issues. You can watch my videos on EC meters and fertilizer chemistry for a little more in-depth review of a lot of the things we've been talking about in this particular presentation. And last but not least, enjoy the great plants you grow by understanding how your fertilizer and your water interact either in a beneficial or detrimental way, and how to make both your fertilizer and your water chemistry work to the benefit of your plants that will give you a higher quality, higher yield, and much more enjoyment of the whole process of growing. So until next time, remember, you need to know what your plants need to grow.